Okay, where we left off was Charles' law. And Charles' law has to do with the relationship between volume and temperature of a gas. I am sure we're all familiar with the concept of how things expand when they warm up and contract when they get cold. That's true to some extent for solids and liquids, but it's especially true for gases. And that's largely because gases, again, have no intermolecular attractions holding them back. So there's nothing to inhibit the movement of the particles. And what happens is that as the temperature goes up, the particles move faster. And they hit the walls harder. Which would exert more pressure. But one of the requirements in this case is that pressure has to remain constant. So if pressure is to remain constant, then volume would have to increase so that there are more square inches on the inside of the container, and therefore there are fewer collisions per square inch. And the overall pressure will remain the same. But the important thing is that in order to do that, the volume has to increase. And in fact, Charles discovered that if you're using absolute temperature, then it is a direct proportion. Volume is directly proportional to temperature. If you're using absolute temperature, like say temperature in units of kelvins. So if you double the temperature, you double the volume. If you chop the temperature in half, you chop the volume in half. If you're measuring in kelvins. You have to remember that though, it's gotta be temperature in kelvins. If you're using Celsius or Fahrenheit, it doesn't work that way. It's not a direct relationship anymore. All right, and this is also the reason why warm air rises, because it has lower density. And so the warm air will rise until its density matches the density of the air around it, which will be somewhat, somewhere up higher above the ground. You can use Charles' law to track changes. Because it's also a fact that for any given sample of gas, volume over temperature is a constant. So say volume before a change divided by temperature before a change is going to be equal to that constant for any given sample of gas. And it's also true if you take that same sample of gas and measure its volume after a change and divide it by its temperature after a change, that same change, I mean, it would be equal to that same constant. So the way we usually write this is V1 over T1 equals V2 over T2. And if this is if this is true, then you can also write it, the entire equation, upside down. It's equally to the T1 over V1 equals T2 over V2. And you can use either form of the equation based on whatever it is that you're looking for. If you're looking for a volume, then you'd probably want to use this version of it. If you're looking for one of the temperatures, then you'd probably want to use this version of it. Basically, it puts whatever you're looking for on top. But you got to remember, temperature has to be in kelvins if you're going to use this equation. So a good example would be if you have gas in a cylinder with a movable piston. And it has an initial volume of 88.2 milliliters. And we heat it from 35 degrees Celsius to 155 degrees Celsius. What would its final volume be in milliliters? Okay, so we need our initial volume and our initial temperature, and we need our final volume and, final temperature. And in this case, we do have to be careful of units because the temperature has to be in kelvins. So when they give us 35 kelvins, we immediately put a star on that because that is 308 Kelvin. 35 Celsius is 308 Kelvin. Our initial volume was 88.2 milliliters, which is fine. That just means that you're going to get milliliters out for V2, which is our unknown. And if you didn't want milliliters for V2, you could just take it in milliliters and do a unit conversion to get it in whatever units you wanted. And T2 is 155 degrees Celsius. And when you add 273 to that, you get 428 kelvins. So that you got to be careful of. We're looking for a volume, so I'm going to use V1 over T1 equals V2 over T2. We want to solve for V2, so you just multiply both sides by T2. That'll cancel it out on the right-hand side, and we end up with V1 T2 over T1 equals V2. V1 is 88.2 milliliters. T2 is 428 K over T1, which is 308 K. Notice kelvins cancel. You end up with milliliters for the units in the answer, which is a good sign. And it would be 123 milliliters. It's possible in problems like this to check the magnitude of the answer to make sure that it makes sense. In this case, we are heating the gas up, so the volume had better increase. The final volume had better be greater than the initial volume. And it is. 123 is greater than 88.2. So that makes sense. It's in cases where two variables are changing that you have a harder time trying to figure out whether the answer makes sense or not. Okay, there's another simple gas law. And that's Gay-Lussac's law. And that's about pressure versus temperature. This is why when we do chemistry labs in person, one of the first things we always tell the students is never heat a closed container. Because if you heat a container that is closed and the gas inside it has no way to expand, the alternative is for the pressure to increase. And generally the pressure will increase and increase and increase as the temperature goes up until the container can't maintain the pressure anymore, and boom, you've made a bomb. And so Gay-Lussac's law is the reason for that. The book doesn't really mention Gay-Lussac's law, and it gets left out of a lot of books for some reason, but it is fairly important, although, like I said, it's kind of more important for lab work than it is in lecture. But anyway, what it says is, as the temperature of a sample of gas increases, its pressure increases. And that's because as the temperature of the gas, of the sample of gas increases, the particles move faster and hit the walls harder. And the result will be an increase in pressure. So unlike in Charles' law, the volume is remaining constant in this case. Or you can state it in terms of a proportion as pressure is directly proportional to the temperature as long as you're using absolute temperatures. Okay, so the temperature has to be in Kelvin. Or you can also state it as P1 over V1 equals P2 over V2. And since that's a ratio, you can also state it as T1 over P1 equals T2 over P2. So if you're looking for a pressure, you'd probably want to use the version on the left. And if you're looking for a temperature, you'd probably want to use the version on the right. And so this is assuming that volume and number of moles of gas are not changing. All right, so that's useful to know. Even more useful in a way is another law that the book for some reason doesn't mention, and that is the combined gas law. This is actually a combination of the three gas laws we've seen so far. So they showed a lot of imagination in naming it. This is a combination of Boyle, Charles, and Gay-Lussac. And it's usually written as P1 V1 over T1 equals P2 V2 over T2. And in this case, this is useful if more than one variable is changing. So let's see. It's also useful in cases which can be solved with the other gas laws. Because if one of those variables is not changing, then you can either just write in the value that it has throughout the experiment and it'll end up canceling out. both the unit and the number would end up canceling out if it doesn't change. Or you can just leave it out altogether. If you look at this, say, for instance, the pressure doesn't change. So we leave the pressure out. Can you see what's left? V1 over T1 equals V2 over T2. That's Charles' law. If the temperature doesn't change during the process, then just ignore temperature, and you've got P1 V1 equals P2 V2. That's Boyle's law. And if the volume doesn't change during the process, then you end up with P1 over T1 equals P2 over V2. That's Gay-Lussac's law. And so you've basically got all of those laws combined into one equation right here. And that's why I like that equation myself. And we can make up an example in which more than one thing changes. So say you've got a sample of gas with a volume of 500 milliliters at 298 K and 1 atmosphere of pressure. So what would be its volume if the temperature were to change to 150 K? So you're cooling it down. That would tend to contract the gas. But at the same time, suppose the pressure goes down, which would tend to expand the gas. And 0.43 atmospheres. So we've got a change in temperature, which will tend to contract the volume of the gas. And we've got a change in pressure, which will tend to expand the volume of the gas. So in this case, we're not even sure which way the volume should go. So this is a kind of problem where it's kind of hard to check the magnitude of your answer. You just sort of have to trust the math. So we have P1 V1 over T1 equals P2 V2 over T2. And we can list out what these things are. P1, you can use any units for pressure as long as it's the same on both sides. The original pressure is 1 atmosphere. The volume at that pressure is 500 milliliters. And the temperature at that pressure, this does need to be in kelvins, which I was nice enough to put it in kelvins, so we don't have to change it. P2 would be the new pressure, which is 0.43 atmospheres. V2, that's the unknown. We want to know what the volume becomes. And then T2 would be the new temperature. That would be 150 kelvins. So if we take this equation and rearrange it to find V2, we have to bring T2 up to the top. So it'll cancel out there. And we have to bring P2 down to the bottom. So it'll cancel out here. And here we have it. P1 V1 T2 over T1 P2. But all you have to do is just insert those numbers now. P1, 1 atmosphere. V1, 500 milliliters. T2, now be careful, it's not T1, it's T2 on top, 150 K. And then on the bottom we have T1, 298 K times P2, which is 0.43 atmospheres. Notice for the units, atmospheres and atmospheres cancel, kelvins and kelvins cancel, and we end up with milliliters for the unit. which is good because we expected a volume. And for the numbers, we got 1 times 500 times 150 divided by, now remember when you divide and you're doing a multiplication in the denominator, you have to use parentheses around both of those numbers. So it's divided by parenthesis 298 times 0.43, close parentheses, and then hit equals. So we get 585 milliliters. So it actually expanded a little bit. So that's handy thing to use for cases where you have more than one variable changing. But like I said, you can also use that equation for Charles' law or Boyle's law or Gay-Lussac's law problems. And so I'm actually going to go back to, no, actually it's on the last page. I'm going to go back to the Charles' law problem we just did. Gas in a cylinder with a piston has an initial volume of 88.2 milliliters, and if we heat it from 35 degrees Celsius, which is 308 K, to 155 degrees Celsius, which is 428 K, what is its volume? And so if we're going to use the combined gas law, we can do that. P1, V1, T1, P2, P2, T2. P1 is not mentioned. And you notice, go through this entire equation, no pressure is mentioned. So we can just forget about pressure. So forget about pressure, and what's left? Charles' law. V1 was 88.2 milliliters. The temperature was 308 K. And V2 is the unknown, and T2 is 428 K. So if we solve this equation to solve for V2, we have V1 T2 over T1, and that's V equal to V2. V1 is 88.2 milliliters. T2 is 428 K. T1 is 308 K, and that should be equal to V2. If we have 88.2 times 428 divided by 308, we get 123 milliliters, which is the same we had before. So you can use, actually, you can use that equation for any situation in which properties are changing. And that is what makes it very useful. Okay, the last of the simple gas laws is Avogadro's law. And this is volume versus number of particles, or number of moles of particles, which we denote as N. And it's a fact, as we mentioned before, that all gases behave the same with respect to pressure, volume, temperature, and number of moles. Okay. And so the identity of the gas doesn't matter. The relationship between volume and number of particles is the same for all of gases. That's assuming temperature and pressure don't change. And what that brings us to is Avogadro's law. This was discovered by the same guy that Avogadro's number is named after, Amedeo Avogadro, and his conclusion was that the volume of gas is directly proportional to the number of particles that make it up. That's assuming that temperature and pressure are constant. And the relationship is the same for any gas. So we're not talking here just about the relationship between a given sample of gas when a change is made in the conditions. This same relationship applies to any sample of any gas, no matter what it is. And another way to write this is V1 over N1 equals V2 over N2, or N1 over V1 equals N2 over V2. You can write it either way. And it just means that if you know the number of particles in one sample of gas and you know its volume, you can calculate, say, the number of particles in another sample of gas if you know its volume, or you can calculate its volume if you know the number of particles. An example of that might be, say, if you have a chemical reaction that produces 0.621 moles of a gas, and it's collected in a cylinder. And the cylinder originally contained 0.120 moles of a gas. Doesn't matter if it's the same gas or another one. And the volume of that 0.120 moles of gas was 2.18 liters. What is the volume after the reaction? Okay, so we're looking for a volume, so we probably want to use the version of the equation on the left. Okay, so V1 and N1 and V2 and N2. V1 was the original sample of gas that was originally in the cylinder. It's not mentioned until later in the question, but it's what was originally there. So I'm going to count that as V1 and N1. So that's 0.120 moles, and V1 was 2.18 liters. N2 is going to be Well, notice what's happening in the question. You're producing 0.621 moles of gas, but there was already 0.120 in there to begin with. So N2 would be the final total number of moles of gas in the tank. So that would be 0.621 plus 0.120, or 0.741 moles of gas. So if we're looking for V2, that's going to be V1 N2 over N1, and that should give us V2. V1 was 2.18 liters. N2 is 0.741 moles of gas altogether, and N1 was 0.120 moles of gas. Notice that moles cancel and you end up with liters as your unit for the answer. And we end up calculating 13.5 liters as the volume. Okay, so 13.5 liters would be the total final volume of the gases in the cylinder. Okay. That brings us to the ideal gas law, but it also brings us to the end of this segment, so I'll see you in a moment.